mostly because I couldn't find any good tutorials on how to make a VLM online. I figured I'd make my own. Um, and then basically share it to the class. I usually do one or two of these every lab because there's so much stuff out there and there's no like nice compressed way to understand how a VLM works. And we don't all have, I don't know, $100,000 worth of compute lying around to run what's online, which you probably still don't understand because it's enormous and complicated. So then this, I'm basically going to go through the slides I was just going through, but now we're going to like step through the code, talk about some of the chunks, why things are be done different ways, what we have to change. Hopefully most people remember like the LLM tutorial from 2 weeks ago, because we're going to base some of what we're doing off of that, but we're going to make a vision transformer first and then try to add language to the vision transformer instead. Okay. Sound good so far? And this is like ask questions. I'll be going over a lot of stuff. So this is basically, we'll go through some of the data because this isn't text, a bit uglier and weird. I'll make a lot of transformations to make my life easier so I can fit this on my laptop. But besides that, everything is kind of as designed, and you could technically like take this and scale it up into like huge amounts and go and train it on stuff. You'd probably want to do some more architectural engineering to get it to work even better. But I kind of designed it for like, here is a data set that fits. You can use larger images. You can use more data. Go wild if you have the time or compute. Okay, so then where do we always start? Any thoughts about where you start when you're trying to come up with a new project or take on some new problem? Get in it? Not entirely. In this case, you've got no code. Sorry. Almost, yeah. I mean, yeah. What's the first word of the class title? Data. What the heck is the data? Before, I mean, everyone knows what text is, maybe by now. It's also up there. So the first part I'm going to go with is, okay, what is in this data set? I mean, we had those VQ, VAE data sets, but everything or a lot of what we worked with in the class has been like, we haven't even really been doing text. Like there's been some continuous values, some other stuff related to that, some tabular stuff. Let's at least look at how to process some images. So anyway, first way to be able to do that is this is just a library to help render images. But basically, we're going to start by loading this data set. This was one of the smaller data sets that I could fit on my laptop. It's going to be used for VQ VAE. You can go check it out later. It's got a lot of examples. It actually just looks like the evaluation or test data set for a particular problem, but it's got about 30,000 examples in it, I think. And then from that, we can just pull how this is organized in this data set is basically there's an image, which is what we'll look at in a second, some question that'll be in text, and some multiple choice answer. So basically, like the data points in this data set is just image, question, which is variable length, and then answer, which is also variable length text. The images are also variable length, but I'm not going to mess around with that today. I've got enough problems already to show like what we're going to be constructing today. And then from that, we can just print like the question, multiple choice. And this, I don't know, to display images in Python notebooks is a bit annoying. So you like write it to disk and then display it again. I really don't like Python notebooks, but I'm happy to go through this today in the structure. Just the statehood of Python notebooks is quite annoying. Anyway, so then like let's just look at one data point, which we can do because it's visual. It's just something like this, which makes some sense. Question, where are the kids riding? Uh, okay, not greatly worded. So I've already got a couple of judgments on this data set, which we can figure out later, but I'm not creating data today. And where are they riding carnival ride? Okay, there's a bit of bad grammar going on there too. We're not going to worry about that much today. And this is the image though. So there are at least only some kids in the image, and it does look like they're riding something that is some sort of carnival ride. So we can probably answer this. But we can only likely answer like the answer part of the question given the image, right? The text doesn't give enough information. So we need to figure out a train and model the process. Something like this. And if we look at like the next example, which we could come in here, maybe I'll just do this. And x is going to equal 1. So we can mess around with this a little bit more, and let's look at the next one as well. See if it's poor or any better. Is this boy a good pitcher? Uh, yes. I don't know that much about baseball to really answer this question, but at least we can start to look through some of the different data points. So it seems like the text is okay. This is probably somewhat representative of the quality of stuff you'll find online. Maybe another reason why vision language models aren't fantastic. It takes a lot of time and money to kind of curate these data sets. Okay, so good so far, right? Any questions? Okay, so this is just like going through the image processing part. Um, okay, but to make my life a little bit easier, so now we've got a couple of images. The next thing, if I'm going to start to construct a model, I'm going to make a very small data set. Like I just want enough to be able to run a batch in my model, which I can mostly use for debugging to see whether or not the model is going to crash. So I'm doing this in just a few steps here. So here, um, I'm using a YAML file to do a lot of the configuration, which maybe you talked about last time. But that's just like the settings for the actual model are stored in here, and they can be shared in different levels of this file so I don't mess up things too much. And according to the internet and some language model, using box here instead of Hydra, which I normally use in my code, is one way to be able to import a YAML file. So this will just give us all the settings from the YAML file here. I'm going to overwrite trim. So I only want 100 points from the data set, not like the 50,000 that may not fit on my laptop. And then here you can do load, and data set name just comes from down here. Name, this, I think I ended up getting rid of this, but I tried to process the whole data set into something smaller. Who cares? And then trim was just helping me not overload my laptop memory when I was pulling stuff from this data set. For whatever reason, this data set uses this key validation. So it loads the data set. Everything looks like it's the validation set. So you have to grab validation set because there's no training or no test in this. Probably helps make it small. And then from that becomes the data set. Okay. And then maybe some people remember this from what we talked about for the LLM training part. So this is world's like pretty much simplest tokenizer here. So what's going to be done is it's not something like sentence piece, but it's basically grab all of the text, sorry, from this data set, and then see which one of all those characters exist, make a list of basically every single possible unique character that is in the data set. So now I've got a tokenizer that at least covers the whole data set, in this case based on character. This one's a little bit different because last time we were doing like that example where it was like some Shakespeare's play. So you could just go through that whole test. That whole data set is like one big long string. The weird part about this is basically there are questions and there are multiple choice answers, which is basically the answer. So here instead, I'm just iterating through every row, grabbing the question and the answer, concatenating them to one string, then looking for unique characters, concatenating all that together, and then you're looking for one unique string. So the part that's definitely a bit different about the text data here is it's not one long book. These are really short question answers, and we'll have to adjust the way we batch and train stuff later to deal with that. And then from here, it's just these are the number of unique characters. So that'll be the size of like our vocabulary or basically our unique tokens. And this will just go from like token to integer and then back for when we want to decode stuff to give some examples. Any questions? Good. Okay. And then the last part basically just goes the other direction. What do we got here? This is only if I want to save the data set, so I think I'll just entirely skip this one for now, so I don't want to worry about saving it. Here, I'm just going to make a different data set because I want to be able to process these images. There's nothing too complicated here, except for the padding, which gets really annoying. But basically, we're going to get three lists, the images, the texts, and here I'm actually going to put the text the answer and the question together into one thing. Because in this case, if we're going to autoregressively produce text, we basically need to read in the context and whatever the next token or letter is going to be. And then later we're going to kind of slice out random chunks of every one of these pieces of text and then just say like, okay, predict the next token, which should be the next proper character leading into the answer. And then the part that's a bit different here, which we didn't talk about a lot last time, is having to deal with padding. So in this case, the input and the output might not be as long as the context length. So then what do you do if the answer to the question is just like 5, even though you've allocated a lot of space for it to actually be able to learn, or even the initial question might be shorter than the context length. So what's done often in these cases, you add a whole bunch of padding, which is just like zeros everywhere to fill in the space in the batch. So basically this padding is up to the phrase length. So I'm kind of controlling for the context length here, such that it's the original text, possibly up to this length. So actually anything over 65 here is going to be too long for the context of my model, and it's not going to work. But for anything under 65, this is going to end up just adding a whole bunch of space characters or a whole bunch of zeros to anything that comes after that point in the data. Does that make sense? I know it's weird, but if we're doing a transformer, we need to have a batch. All the batches need to be of the same size. And if we don't have characters, we need to fill in with something so that all the batch and inputs are the same size. Okay. And then in this case, I'm just going to take each one of these images, append them to this long list with one other step here that'll make a bit bigger. But this is also just to save some memory on my computer. But here I'm just going to reshape every image to be 64 by 64. If I don't do this, there's no way this is going to run on my laptop because every batch is going to be like 30 gigabytes. And I've only got a little 44 gigabyte GPU on my laptop. So this is, for the most part, to make it so this will fit within my memory requirements for this example. Yeah. Can I stream the batch instead? You could, but it trains much slower that way. Like to be able to process a batch. The way I'm designing it here, I can usually go through like 200 a second. Well, here I'm only making one batch, but I've got about 30,000 examples. So the one reason that this can also run on my laptop and like train within 2 hours is actually I'm doing all this so I can fit all the images and text on my GPU. So there's no streaming, there's no batching. Yeah, if you want to load up like Hugging Face data sets and stream this later, such that maybe it doesn't fit on your GPU, that's part of the architectural changes you'll have to make. Uh, I did not have much luck doing that. It was still like way slower than I wanted it to be. Okay. So yeah, I'm trying to, this is also like really doesn't use any extra libraries. So you can see what's going on. And then if you want to build on this, yeah, data set is probably the first one. So you can at least make it bigger. And then model size, you can grow as well. That one's much easier in the code. Okay. So yeah, and then this here. So I'm going to convert all these to torch tensors. So if you've got a little bit of space on your GPU, this will all be stored there. This will all train really fast without having to worry about any like memory allocation or swapping or streaming of data. Okay, and then that gives us a bunch of examples. So this should hopefully still work. Doesn't take long. Most of it is processing data, although some of this stuff for downsampling images is a bit slow. CUDA really does not like me today, so I'm probably gonna have to like kill this again. Restart. Okay. I think this is all pretty much self-contained, so I can have to run this again. Nope, data sets is not defined. This is one of the reasons I'm not always a big fan of Notebook. Okay. CUDA unknown error already this early in the game, huh? Loading mode is lazy. Initialization is true. All right, I guess I'll just be lazy really early on and just change this to CPU. You're welcome to go mess with this a bit later. So restart again. Run this to be able to get the data set. That just like loads the Hugging Face version. This will process some of the data, take a little bit longer. So here's a bunch of examples of stuff that's encoded for. So this is the encoding of the text, whatever it was beforehand, rather than the actual example. So here's our text tokenized into integers so that our transformer can read it. This is just one of the images as the data that we're so familiar with looking at. Remember that images are always just like unsigned numbers between 0 and 256. So if actually we want to do this well, somewhere in the code, we should divide by 255.0, which we'll get to. And I've only loaded 100 examples like onto my laptop for training right now. Okay. And I've abandoned basically CUDA for the moment. Um, so basically the next part or the first chunk of this is how to create a vision transformer. So we're mostly going to focus on the image-based stuff for the next little while. So here, the first thing we're going to talk about is, okay, there was something you can construct an encoder or a decoder for a transformer, depending on which part we want it to pay attention to. For the stuff we were doing for text 2 weeks ago, we wanted to be able to make uh, basically just a decoder. Like it should only pay attention to text it's seen in the past. But actually, not because we're processing images, it's mostly an encode. Like we need to see the whole image. It doesn't get processed in order or causally. It needs to look at every single chunk. So before, when being able to look at like our key query and value, we would use this max fill trill part basically in order to turn this into a decoder because all these zeros in the attention map basically say, okay, don't pay attention to patches that appear future in the image, which doesn't really make sense because this is all one image. It's not being fed in chunks. So luckily, to turn something from a decoder into an encoder, it's a pretty easy step. We can just get rid of this line of code. So now this won't zero out all those other chunks on the attention map. It can attend over wherever it wants in the image at any time in order to be able to look at things. And then from that, oh yeah, then we can look at it instead. And now there's at least like some probabilities for the rest of the attention maps for that particular part of the weights. Yeah. Does that make sense? Questions? Okay. Because we're going to revisit this at the end, because this actually gets really weird when you start to make a VLM, because now we're eventually going to want to have an encoder for the image, but then a decoder for the text. So we're going to mess around with the way that this is masked later on when we get to that chunk, because we want to be able to autoregressively produce text, but always pay attention to all the image. Okay, so that's why I'm bringing this up, because we're going to revisit this about 2 more times. Okay, but this just basically like makes some linear heads, uses this trail function again, value, look at the shape. All right. So then if you remember, we're not changing much about the transformer code from before, like a transformer needs a head. Now this forward function here is the same that we were just talking about here. That's actually doing the attention without like any of the random stuff. So it's the same as this. For the head node and the forward process. So this is basically doing all this, removes masking for a encoder in that case. Okay. And then the rest of the stuff is still the same, multi-head attention. So stacking a bunch of heads together, doing a little bit of dropout just to help keep our model from regularizing too much. Also adding a little bit more dropout on linear layers. And then a block is just a multi-head attention block with a couple of chunks of layer norm to help it be a bit more stable. Those aren't really important right now. Okay, so like most of this chunk is the same as what we did for the previous transformer from 2 weeks ago. Like the text part is all the same. I'd only changed one line, which was just I removed that masking aspect. So now it's an encoder and it doesn't ignore anything. It's also what's sometimes called like a non-causal model. And a causal model is not supposed to attend to stuff in the future. It's not how causality works. Okay. So the part we're going to basically start to get into that's next then is being able to tokenize, or like patchify images. Uh, nice as a concept, a little bit annoying to program to be able to chop up all the images into like the right size chunks to be able to train your model to. Fortunately, there's a couple of nice little libraries that help do this, although they look a little bit fuzzy in terms of easy way to understand them. So we're going to do this process where we're going to break up each image into each of these chunks that's a patch. We're going to use eigen here. So if we remember with this, so this function is just called get patches. So this takes in an image, to be honest, like a whole batch of images, and it's basically going to rearrange all those images into instead a whole bunch of patches. And each channel, if you remember, channels for an image are normally color, but now each channel out of this is going to be a new patch vector. So we're going to have lots and lots of channels technically depending on how big our image is, but it's always going to be 64 by 64 in our case. So we should have like 8 times 8 patches, which I'll get to for some of the numbers, but that's mostly because I think in here somewhere, channels, yeah, patch size is 8. So this basically means 8 by 8 pixels. That's how much the size of the patch that at least I want to be able to process over these images. They're kind of small images, so this is an okay patch size. Um, and most of this is all just text to describe what it does. The part that comes from eigen here, or einops, sorry, is basically how to do this rearranging. So the formatting here is a bit odd, but if you're a bit familiar with regular expressions, this basically means the first number, at least for the way I organize my data, is batch. First number is batch dimension. Then right now it goes height, width, and then channel. So that's the way it's currently organized as it's going into this rearrange function. And then this kind of regular expression says what I want out of this. So now when this comes out, I want still batch size in the front. Then we're going to have height times width, number of channels. In there, stuff what used to be left over from the height and width into this chunk times the channel size. So this is going to rearrange something that was in 4 dimensions, put it into 1, 2, really like 3 dimensions instead. And then from that, you can specify P1 can be the patch size and the patch size to help add some constraints. So this is doing all the magic of doing all the rebatching around to get a patch. Yeah. Does that make sense? Yeah. It can determine what those numbers should be based on this process because there would be possibly different sizes and dimensions here. Like this should all have the same number of like bits in and out, but this will help control the shapes properly for knowing the patch size, something like that. Yeah. And then what did I do here? Oh, you can ignore this. That's left over from a prior chunk of code I wrote for a robotics project. Uh, yeah. So this would just be different. Okay, I mean, if you want to know this part, which we won't really be doing at all for today, but if you wanted to be able to patch videos together, so this is if I was stacking many images on top of each other. Now you have to patch in basically, figure out how to chop up everything for each patch, now for every image. And then I would extend on this dimension also includes like the history size for however many images. So now this will be really long, lots of patches. So yeah, there are RGB channels here. In this case, they'll be stacked into this part. So this, does it end up going R, like basically everything in the patch for red, and then I think everything in the patch for green and then blue, all into one long vector. Yeah, I think 8 times 8 times 3, so 192. Yeah, sounds about right. Okay, does that make sense? This is kind of the painful part. Make sure you test this function, especially when you go to make something like this. So in this case, what I'm doing is I'll run this function just to load it. And here, basically, you can reverse engineer this process. So I'll get the patches and then I'll grab the shape for one of them, and then I'll basically turn it from one of the patches back to an image and draw a bunch of lines in it, and it should look the same, I hope, or I've messed this up. So, oh, don't worry. Doesn't end up working out too bad. And this is to be able to reconstruct the image and draw little lines across it. And then you end up getting this original image. So it's a bit small, but if we all, I think it's this one, if we all squint pretty hard and remember that the first image was those kids being in the back of this in like one of those carts, we can kind of see that. And this is how the thing actually gets reassembled after being patched into different chunks. Yeah. You might ask, hey, if this is not working too well, or like you can hardly make out the kids in the background of this image, yeah, well, just ignore that for now. So if you want to do that, get a bigger GPU and use larger images. Yeah. Uh, I'd probably use a bigger patch size for much bigger images. A little bit, but in this case, I think what I was looking at earlier, because I'm comparing some of this to at least like Polygemma's model. I think what was there? I think their patch size was a little bit bigger. No. Normally people use patch sizes that are a bit bigger because 64 by 64 like pixel images are pretty small. It's really hard to understand much of what's going on in the image because they're that small. It's like the minimum image size you can use for it to be useful, basically, is 64 by 64. I think normally a lot of models are using more like 16 by 16 pixel images, or sorry, patch sizes. Yeah. It's a good place to start. Although I'll even say it seems like the pattern is more to like pick your patch size, like 16 by 16 pixels. And then your model might have different sized images, but it'll always patch stuff into 16 by 16 bit chunks. So there your hyperparameters are a little bit more robust to image size. Yeah. And that's, I think, specifically what they did here, or even they started out training. Yeah, this one started with like 224 pixel images and then went up to 448, and I think even another version of that too. So they kind of like pre-trained it on smaller sized images and then started scaling it up and making like the context length longer. Okay. Uh, Okay, so that's this image, somewhat interpretable for now, but again, you can make the images a bit bigger later if you'd like. I think it's actually pretty easy because I processed all the image data from above. They're all 64 by 64. I think the codes, like you can go in and change the image size if you want in this. It should still work. It will then start to consume a lot of memory on your computer because it's going to go up quadratically in terms of your image size for how much GPU memory you need. Okay, so that gets this. All right, and then this gets to one of the first chunks that's weird. Um, Being able to make the positional embedding. So I guess I can just click on this one. So like in the Vision Transformer paper, one of the things that seems to be important for the design for this, it's not really these parts, is also being able to use some positional embedding. So here the idea is to, along with every basically patch for every image is a unique identifier that mostly helps the model figure out where that actual image, where that patch is located in the image. So here you can kind of see after the model is trained, it's kind of learned that the top left patch looks like it's in the top left part of the image. And this at least gives us some understanding that the model can figure out relative locations. Without this, the transformer really can't infer kind of like where locations are in the image. So if you're only doing classification, maybe that's okay. But if you're doing anything like VQA, where it seems to be mostly about where things are in the image relative to other stuff, you definitely need to have relative positional information like kept in the way the model is designed. At least though, I don't know, the first version of this that I found like for this, this positional thing is really simple. In this case, it's just a sign function that'll give you like a unique floating number depending on like the sequence length for the whole context. It's pretty easy. You just come up with some, it's basically another tokenizer of sorts to find like unique positions for all the items in the sequence. And then the network can learn to pay attention to that ordering and pick up on those numbers. Yeah. Does that make sense? Okay. Great. So I think we'll skip the Sorry? Yeah, like in this case, it's basically given some sequence length, and now this is going to be the length of the number of patches here. Generate basically a unique floating valued number that'll uniquely identify each of those patches. So now it's just kind of like saying there's a unique key that corresponds to each one of the patches, and this will generate something unique because the sign function basically goes all unique numbers between like the first version of pi or something like that. So then you take your sequence length, stretch it or squash it basically into the length of pi and generate a bunch of unique floating point numbers. But whatever the sequence length is, it'll generate something that kind of equally spaces out the sign function across sequence length. And then we'll add this basically to part of the transformers processing. Yeah. Else, okay, all right, yeah, maybe it is cosine after J in range D. Um, Positional embedding. Oh, D is the size of the embedding. So I guess it's going to generate for different dimensions of the embedding size. It's going to generate a different function, a different number. What does that mean in this case? Hmm. D. Yeah, I don't know. Looks like it's basically going to generate a different value for D as well. And that'll be the different dimensions of the embedding vector as well as the tokens. Okay. Um, what is this all about? Oh, this is just, okay. So now, supposedly, we can get enough data for a batch. Um, Being able to get a batch is actually pretty easy in this case. So here, this is a bit, okay, mostly normal. Basically, just get a random integer for the length of the data set, so it'll randomly pull out some numbers. Grab the image for that data. For the moment, I'm just going to set that like this is literally just classification at the moment. And I'm going to set the class as whatever the integer value is for the last letter that's going to be a part of the actual text. This may be unique. It's not perfect, but this is mostly just so that I can do some training right now and it won't crash. But this isn't actually our target value. It's probably okay, but I bet there's going to be some unique changes in identifiers. So this just helps get text. Why? Because basically this model needs some images and some targets that are a class. Here I'm going to divide this by 255. So now all of these images are between 0 and 1 in a continuous space. And it's a little bit better for deep learning. Okay. Good. Any questions? Okay. Great. Most of this to batching. And then this last part, just to load this is just like estimating the loss. So here, like a gradient won't be computed. This will just be later for figuring out how much the loss is for like plotting, things like that. Not very important for this chunk. Okay, and then actually, all right, so then how do we construct the vision transformer? So we've got the models. We're gonna make this buffer. So here's our computing our positional embeddings for some image. So this is going to be our shape times 2, because basically everything's going to be 8 by 8 times 2, and then plus 1. This is the one that's always a bit odd, but basically for a vision transformer, the very last token, or at least somewhere in the system, is what's called the classification token. So all the rest of the tokens are basically the actual image input. And then to help the model infer what the class should be given all of that, there's kind of one last sort of empty-ish class token given. The idea is that token will learn what the actual class is after it's read everything, and then we just read out the information from that token. So that's basically the size of the context here is always like number of patches plus 1 for this class information. We'll use this as well a little bit, yeah, a little bit later to try and infer some other stuff related to like autoregressively predicting all the text. And then you have the number of dimensions for the actual embedding that we were talking a bit about earlier for how this positional embedding works. Okay, and then like class tokens, just going to be a random parameter right now. The input size, at least for the part that's processing images, kind of what we were talking about earlier. So this is just the size of the image. So remember, this is the channel dimension, and this is patch size times patch size. So this will give us our actual patch dimensionality. And then our one model here that basically takes in this input dimension, our one layer, and then converts this into a linear map. But now it's at least in the embedding dimension of the transformer, however big that is. So you can make this bigger if you want to use more compute, basically, and have your transformer store some more information. Otherwise, this just goes from whatever your actual input dimensionality is to your embedding. Okay, makes sense? Okay, good. Um, so then from this part is kind of basically the same for the transformer. Make a bunch of blocks with some extra dropout that all work together. And then at the end, one last linear model that'll take the output dimensionality, do softmax, because it's just supposed to predict the actual class, or basically the integer that's going to correspond to the token, which is going to be a character for us. And then that's just the last layer for the model. Any questions about this structure so far? Yeah, it's really similar to what we did for doing like the language, or like just the text transformer. The only real differences so far is this positional embedding. I think the classification token is the only other thing that's been added. Otherwise, almost normal transformer here. The only thing that's going to be weird is, okay, the input size is a bit different. Okay, and then the forward process is just get all of the patches, take this linear model that reads in the input dimension for each patch. This will now be a lot of patches here. So just like there are for individual characters, concatenate basically all the stuff together with the actual class tokens. Okay, in this case, it looks like the first token here is going to be the class token rather than the last token. And then you can repeat these positional embeddings and then just add them to the actual output. So this is the part where you can take the out and literally like add the positional embedding to change the values a little bit. And that's how the positional embedding is used here. And then just feed this through however many blocks that you have in your transformer to get the output. Grab, in this case, the very first token in this process. And then that one ends up being the classification token. And then from that output, use that NLP that we designed up here that does linear and softmax. And then that'll give us whatever we're going to use as the logits for our loss. So, is the output, or like the highest probability of the thing here, actually correspond to the target that we want to choose? If not, okay, adjust the model weights to predict something closer to that target. Okay. Questions? Good. Totally clear. Everyone's awake and has had lots of coffee. I know there's a fair bit of code there, and some of this is maybe a bit better in diagrams, depending on your preference. But this is, in this case, for the forward function, really the only thing we've added here is now this positional embedding. Otherwise, it's the same as what we talked about 2 weeks ago for just a normal transformer model. Okay, great. So I guess can load this as just our vision transformer model, and now we can do a bit of training, create the vision transformer, load some optimizer, and just basically get a batch, train the model, backward step, do this repeatedly until we're done answering questions. Watch it crash because I probably forgot to click on something earlier. No name for block, so I probably didn't click on this yet. Okay, and then go back here, rerun VIT. This should hopefully train now. Okay, so there's only, this model is pretty small in this case. I'm only using an embedding size of 256. And then, oh, there we go. It's on CPU right now because CUDA seems to complain when I load torch and set the random seed. And if I try to do that again anywhere in my code, it just gives me some weird cryptic error. So I'm using the CPU for right now. If you want to run stuff later, there's like a final version of this code, which you can just, like this is the non-notebook version where I coded all this up. Just go ahead and run that on the GPU. Sure. Yeah, so this is what I shared on Piazza. So if you want to mess around with it, go ahead. So this will train. It's a bit slow because now it's on my GPU and whatever, GPU related challenges, or at least CUDA related issues. But yeah, the training process after designing the model isn't too bad. It just takes a little while to train. Uh, it's not using okay, it's using a fair bit of CPU kind of compute on my laptop, but it's not too bad. But it is already consuming a good chunk of memory on my laptop just to load that small bit of the data set. Okay. Yeah, good. Other questions? No? Okay, everyone wants to get to the ugly VLM part of this? All right, fine with me. Let's go ahead. So in this case, you can go ahead and let this train. So this is just a vision transformer. Now we're going to take this vision transformer and add some text to it. So the first part is to be able to add some text questions. So this is basically the same data loading code that we already had from before. I think it is actually exactly the same. I'll run it again anyway. So this is still going to put text together, which is text, which is going to be a combination of encoding the question plus the multiple choice answer together into one thing. So we just have a string of text that makes up what should be predicted related to this particular task or image. Okay, so first part that already starts to become a bit problematic. So we're going to need to figure out how to attend over this text. The first part is that we at least need to add to it. So now here we need to compute the context length, and it's going to depend basically on the original image shape. So this is the size of the context we had from before. The number of patches plus the classification token. And then this block size here is basically how many tokens do we want to use for text. And now those combined together will determine our context size. So if we go back to the slides I was talking about before in the class where you could do early fusion, I'm doing early fusion here, but this is also one of the weaknesses of doing early fusion where you combine stuff together. And it can result in a really long context because now you can have really long text here. You can have more images if you want to include sound or something like that. This gets longer and longer, and transformers are slower and slower depending on our context length. So here, Emily's just using some of the config files to get this. So if I want, I can alternate a little bit for the size of the actual context and how much text it pays attention to when learning. Do some dropout. Okay, and then the last part here, I guess on top of this, Uh, yeah, that I suppose I was going to talk about a little bit more later, but oh well. So now here, if our image is like 64, like the original 64 tokens, we want the model to basically pay full attention to all the stuff in that image. And then for things that it's decoding, I want that to decode those things causally and only be able to pay attention to whatever it had generated from itself in the past and then trained in the forward. So in this case, it's just so up to index 64, that stuff can all be fully attended, no additional masking, full attention, and then things after 64, all that stuff should then be like causal attention for being able to predict the text instead. So just a little, I don't know, a tiny bit of fiddling here with just being able to do this masking properly. That's really the only line that's actually changed in this code. Everything else is pretty much the same. You should probably be going like, okay, professor, but this is really bad coding style to put 64 in here, and instead I should be using this. Yeah, probably. I'm not too worried about it at the moment. Uh, okay, that's the only thing that's changing. So I changed the definition of the head a little bit to control the way this masking is going to work. It really reflects what is done inside of like the poly Gemma paper, which has a nicer diagram. So this is a green check mark means like full attention. So the images can attend over every image chunk in the attention mask and possibly for some of the input question. But then things that are part of the answer don't attend to stuff besides like what it's been able to see so far. So these can't, like it can't attend to part of the answer. That wouldn't make any sense, right? It can't look at what the answer is to determine what to predict. So this is just a nice diagram that's just basically starting from the original attention maps and then so this stuff is all like fully connected and this other stuff is not where we're going to use trill to mask out a chunk of this attention. Okay. Does that make sense? Okay. This is really the art of using transformers is like, okay, where can we go in and like override the attention masks and try to get what we want? All right, great. So then from here, um, okay, yeah, we already canceled that part. Did some data set training, good. So this is really we're only just training this one head. All the other multi-attention pretty much stays the same. I mean, if you want to be really hard on me, sure, I added an argument here to be able to pass in the config file, but that's just to be able to compute the context length, do the masking properly. Besides that, it's still feed forward, blocks, everything's the same. We will run that though. And then we'll get into making the VLM, which is now a teeny bit different. So now that we've done those other chunks, we're going to have to make our positional buffer. Now this is going to be a bit bigger. So we've got our embedding, we've got our image plus, so those are our image tokens. And now basically whatever max block size is, which is just like the context length for text, is going to be used for this. And then that other dimension for being able to do the embedding. So now the number of tokens here should always be, yeah, like block or like image size and then text size. And I'm also doing that ordering. Uh, Sometimes it matters whether or not this information is fed in images versus text first, but it shouldn't be that important to how the model's trained. Just remember which way you did it when you go to use it later. And now here we're going to have the token embedding table that's going to go from vocab to our embedding size. And then we've got our class tokens, embedding size. So everything needs to map to this embedding size. This is like the language size of the transformer. The same thing for doing this. It's not for pose, but this should also be for our dimensions for doing the linear map for the model. I think both of these can actually be removed, and that should be fine. Ah, okay. And then blocks again. And now we've got something here for our MLP and C output. Okay. Any questions about this? So now really the only thing I've introduced or like reintroduced is that token embedding table for the language. We haven't used it yet to actually be able to compute stuff, but now we've got it on hand, just like the transformer that we had from before. Okay. And you can ignore some of this stuff, which is just trying to make the model work a little bit better. So then in our forward model, it still get patches fast, although now this should use this token embedding table here to take the text, get out the goals in this case, which is just the embedding. This will take the patches and now concatenate together basically these observations plus the embeddings for the text, and then the last classification token that's added to this as well. So basically this was really what we changed in the forward function, is just do a longer concatenation for what should be fed into the transformer. Still good? Questions? All right. Still the same loss, still the same output. So really all of this chunk is the same. So there's just essentially really a lot of repeated code in here, but it's just the best way I can organize. Okay, the only thing now it's going to be a bit different, at least for the vision transformer, this part wasn't there because you don't usually start to generate tokens and like patches that come out of it. But if we go back to like the LLM little GPT model from before, it had a generate function. It's like feed in now. It's going to take in an index and an image and then basically generate what the next token should be. And then we can decode that into text. So that basically the image will always stay the same. And then we'll just keep feeding in a chunk of the context, generate the next chunk of that context, kind of slide this window forward. Now we've got that character that was generated. And then basically now train the model to, or ask the model to predict what the next token should be in order to do that, and then move one step forward. And we'll kind of generate an answer for this by slowly taking the output from the model. Possibly it'll start hallucinating stuff depending on how well it's trained, but it's going to now take as input stuff that it generated. Okay. That makes sense? Okay. This is where all the danger happens, really, because this is most likely going to cause problems because it's going to start generating stuff from itself that wasn't necessarily in the data. But this is usually how you'd start to like generate a whole answer based on itself. Okay, how are we doing? Mhm. All right, let's get started on the last bit. All right, so we left off on generation. So now we're just going to be like figuring out how to get a batch. It's just a little bit different this time. So all the stuff above this is the same. We're just going to get images. The last part here, we're going to be grabbing the text. And as I was mentioning before, we just want to grab a chunk of the text. So the text could be, to be honest, it could be huge. Like it could be thousands of characters. But in this case, our context length is just 64, at least as for chunks of the text. Right for the fine max block size, only 16. Okay, it's actually pretty small. So this is just going to grab chunks from this text that are basically, in this case, 17 pieces long. So we've got one thing to predict. From that, stack all these images together. Y is going to be the very last character in each of those like chunks of text. And then the input here that it's going to be training over is just the stuff before Y. So basically picture this big giant matrix. The last column is going to be Y, and the first chunks of it that are X are all going to be the inputs to the model. And then the rest is to like divide by 255. Makes sense, right? Basically, the only thing I'm doing different here is now for each model, it does get a little bit tricky because now the lengths of the text could be different for each of these. So it's kind of now go grab a bunch of text, check the length of it, then pick a random integer basically inside of the length for each of these text chunks so that it all is actually inside of the actual length. That doesn't go outside of the dimensions. So you can help eliminate padding issues. And then from that, just make sentences. So the only extra weird part is here. This is going to grab for I based on the length of the text. Because now every single like question answer group that's put together can have a different length. So we want to, for every question, find its length and then pick a random slice of that window so they can all have a different length, unfortunately. So this is one of the weirder parts about at least the data processing for this model. This estimated losses is exactly the same. Okay, and then if all this works, and in the unlikely case that notebook is being, Yeah, Notebook is being pretty nice to me today. This should train. So I didn't change anything about this, much that's different. Now I'm going to use that like generate function so we can see like what is the model generating as it's being trained after every 100 steps. It'll take like a random pull from the data set, grab the first option, start generating from that and see what it looks like. Besides that, the only difference is now the model also takes in like the text as part of the structure for the input. And we'll see whether or not this will work. I'm sure I've missed something. There's more of an issue with next is out of range in self. That's definitely how I feel some days. Anyway, I don't think I clicked play on the VLM model. Yeah, I think it's this. So that one and that one being able to get the batch like we just discussed with some extra notes. And now let's see if this will train. Not being too nice to me today. Oh well. Fortunately, I prepared for this because this one is when I get to the end and whether or not I clicked on things will either work well or not. So at least at the very end of this, like Python Notebook is basically just all of the code, all in one file, just so you could be able to run this. So all this stuff is the things we've already talked about already. And then this bottom chunk is still the same model. And then here's all the same parts for just being able to decode. So this is the different main function at the end of this one file that'll import everything properly and not run into any more kind of notebook related challenges. So this one should do fine for training, even if it's on the CPU. So now this is training. This is going to take the image and text as inputs. It's still got the classification token. Then it's going to generate a little bit of output from the model so far. And this is like essentially all that is needed for basic version to be able to construct the vision language model. And in this case, fits pretty well on my computer. Obviously, if you have more data, you can start to be able to make the model parameters and like model size bigger, more blocks, more transformer layers and nodes as well. So you could just go in and here and start to change the number of heads and the number of blocks if you want to start to make your transformer bigger. But besides that, here's an example of like, so this is probably the ending of some chunk of a question here that it's being trained over. And right now it's clearly just generating hallucinating garbage, but it's just poorly trained for what it is so far. And then after a lot of training, it does end up performing okay at stuff that it can predict. Still a bit odd. Does this make sense though? Any questions so far? Okay. At least I'll note that. So this, as you can kind of see, is one of the reasons why we probably want longer context. Because right now this is just processing half of a sentence. So it's not even including everything that it needs in the sentence to understand what's going on about the question. But you still basically would use the same model. All you'd probably end up doing is going into this. Okay, go on the fly, see if this works. You can make this text block longer to something like 32. And then for at least for this one, this should still continue to keep working because it's going to grab all the data, make the parameters a bit longer. I think the model size grew a little bit just because of the extra tokens, but now it should hopefully generate like a sentence that's a bit longer and includes more of the context. But now it also makes the model larger in order to be able to handle those longer inputs. Yeah, so now you can see, should the car go or stop? And then stop is the actual answer, and then it can generate a bunch more information. So now this is at least has enough context to capture the whole question. Okay. Makes sense? Okay. And then what was I going to do? I had one last thing to basically be able to discuss for a second. I guess it's just, oh yeah, a little bit about the training process. So this works okay-ish. Takes a little while to train here. So this is just like after training this model for a couple of hours with only like the 16 token size window, it starts to at least get a little bit better at like last haircut, recent, at least it's starting to construct some words like looking rather than just totally random garbage that it starts to generate. things like table. So basically, this is the input question here, and everything beyond that is what's being generated from this model feeding off of its own like generated outputs. So after a good bit of training, it does get a little bit better at even generating some portions of the question and then being able to do some stuff with the answers. But this happens after, like a little bit of training in weights and biases. Um, that's not too bad. It took me like an hour and a half to be able to train this. I admit it's not like perfectly trained, but it is getting okay-ish performance in generating some words. So if you want to be able to train it, if you let it run for about an hour and a half and have an okay-ish GPU or something like that, you should get some okay performance. Okay. Any last questions? Oh, probably even more than this. A decent loss is probably something like zero point 0.1. So it'll still take a little while to get down. Also, I didn't really do any of the stuff that we should do for this model, which is find, like keep a little bit of the data out so you can actually use it as like the test set or like the evaluation set to see how the performance is doing, which you can do easily just by like, batching up some of the data and adding it to it. But in that case, you can actually check accuracy a bit better rather than just loss. But yeah, just be careful to not look just at the loss because we might start overfitting a good loss and the model actually does poorly and won't be able to answer the stuff outside of the data set. Okay, great. Yeah. Any other questions? All right, that's mostly it for today. Like you can go and dig into this some more. I know you're working more on like homework assignment 6 or whatever it is. I'm doing some fine tuning now. So I don't know, a bit of this stuff is related, but normally it'd be like taking this model. We won't do fine tuning of vision language models. That's already complicated enough as it is. All right. So that's it. Take care. Feel free to ask questions because I posted some Piazza or make pull requests, or I'm sure there's a couple of errors that you can probably improve on or try using Hugging Face. Yeah, or build on it afterwards. But this is also becoming pretty popular-ish stuff. So it's good to have this background. You'll most likely do more fine tuning on these types of models in the future. All right. Take care, everybody.